Okay, we will start talking about sequences and series. And notice that when we talk about a sequence whose terms approach a limiting value, then we are talking about convergence. So that's something for us to keep in mind. And notice that we have our sequence that here they have multiplied out. This converges to 0. And so we say that we have a limit as n approaches infinity that's going to go towards 0, which we see if we did the limit back over here with our original, that limit as n approaches infinity, we see that does approach 0. So the next part though, if we do not have a limiting value, the sequence is said to diverge. And notice what is classified as divergence. We get infinitely big or small, or it oscillates between two values. That would be divergence. Now notice that we are making comparisons between different types of functions and sequences. So that is something for us to keep in mind, that we are making those comparisons with functions that are modeling what the sequence is doing. So let's say if f is a function, and notice as x approaches infinity, that function has a limit L, and notice that our sequence really models what the function is doing for every positive integer, and then our limit of this sequence is also L. Okay, now we're going to look at a sequence that converges, has the nth term converging to some limit. So that's kind of a lot for us to remember, but we'll get the hang of it. A series that converges has the sum of its infinite terms converging to some limit. So we're going to look at some of these partial sums and see what we are getting ourselves into. And we're going to say partial sum because I'm not going to sum up these infinite terms, so to speak. We're just going to look at a partial set of them. So let's see, the sum of our first term, well, our first term, remember we are starting at 0. So that's going to be 1 over 2 to the 0, which is going to be 1 over 1, or 1. Let's see, so our second term, which means n is 1, but now we're looking at our sums. So that means I have my first term still, plus 1 over 2 to the first. 1 plus a half is 3 halves. Okay, so we notice this is building. So for our third term, we would have our first two sum, which is 3 halves, plus, and then the other would be 1 over 2 squared, or 1 over 4. So it looks like that's going to end up being 7 over 4. And then for our fourth term, we're going to have our 7 over 4 plus, and then we're going to have 1 over 2 to the third, or 8. And after we do all that math, that was going to be 15 over 8. So there's kind of a partial sum of what's going on. Now, we do need to talk about, well, what is the nth sum? What does that look like? Well, let's write out our terms and see if we can figure out some kind of pattern that we had here. So my first sum we had was 1. My second sum was 3 over 2. The third sum was 15. Oh, did I miss? First sum was 1. So it looks like I'm missing one. What was our third sum? 7 over 4. There we go. We'll look back up and see. It was 7 over 4. And our fourth sum is 15 over 8. What a mess we've got here. But I need to write my sum as an nth term. Yeah, piece of cake, right? something we have to keep in mind here is our n values in the original started at 0 and it went through infinity. So when we're writing this in terms of n, we really have to keep in mind that our n value and our term value, they're one off from each other. So in the denominator, notice when we first started going through and listing out our sums, that very first term was really 1 over 2 to the 0. And n is starting at 0, so it might be okay to go 2 to the n there. And so that would be 2 to the first, 2 to the second, 2 to the third. So I think that'll be okay. But now the numerator was a little bit different. Let's see, we had a 1 there. And, let's see, we can do, it looks like these are all 1 off from a power of 2. So, like 2 to the third is 8. 2 to the fourth is 16. Let's see, 2 to the second is 4. So it looks like if we're still in terms of n, we're going to have to add 1 to get it to line up with my term itself, but then minus 1. So let's check and see, does that work? So here n starts at 0, so 2 to the 0 plus 1 is 2. Minus 1 is 1 over 2 to the 0, which is 1. If we plug in our next term 1, that should give us 3 halves. So let's plug in 1. Again, we're 1 off because our sum starts at 1, but our n value starts at 0. And let's plug in our next version. So that's going to be, let's plug in 1. So 2 to the 1 plus 1, so 4 minus 1. Yeah, this is going to work. All right, so we have our sum written as an nth term here. We have it all collected, and it's, let's see now, what would be the limit of this? That's our next question. So let's see, what would that limit be? Well, let's find our limit, and my board is messing up. Sorry, folks, technical difficulties. So let's see, we have the limit as n approaches infinity. So n is approaching infinity. I almost wrote 2, yay me. And we have 2 to the n plus 1 minus 1 over 2 to the nth. Well, let's see, we can break this apart if we need to. So we have the limit as n approaches infinity of 2 to the n plus 1 over 2 to the nth minus 1 over 2 to the nth. Now you can always do that as long as you have one term in the denominator. It's no big deal. And let's see, as n goes toward infinity, well, this is going to shoot off to 0, so we don't have to worry about that term. And we can break apart this term. That's 2 to the nth times 2 over 2 to the nth. Well, those values are going to cancel out as well. So it looks like my limit value is 2. So again, we can go back up to the previous statement, which tells us to remember that a sequence that converges has its nth term converging to some limit. And so we notice we found that convergence to some limit. A series that converges has the sum of its infinite terms converging to some limit. And so we've just shown that. Okay, now we have our tests, or just different things for us to remember for our convergence tests. And there's several different ones out there, and we're just going to grab some of the major ones, and then we'll come back and look at some more of the minor ones. The first thing that we do need to look at is really for an nth term. And so notice that this is really, if you look at our next line through here that we have, that the nth term test if the sequence does not converge to 0, then the series diverges. If the sequence converges to 0, it doesn't necessarily mean that the series converges. So you're like, well, why are we even looking at this then? And this statement right here, it's really looking for divergence. And it doesn't take very long to do your limit as n approaches infinity and just very quickly see, well, will I have some kind of limit value, or will I shoot off to infinity? So let's look and see, what does that mean for these problems? Well, example 2 is a great example for us to look at. Let's take in account the limit as n approaches infinity of 4 to the nth power. Well, this is going to be like crazy big, so this shoots off to infinity, so very quickly we can say, hey, this diverges, so you don't have to do any more to it. But let's look at B, and we've already talked about how this series does diverge, but if we do our nth term test, we do our limit as n approaches infinity of 1 over n, notice this goes to 0. So it does not mean that this series converges, it just means that we don't know. We need to do another test. We need to investigate a little bit farther with this. So I'm going to put do not know. We do not know. And again, just because you get a limit value does not imply anything other than, hey, this may or may not converge. We need to look at more tests. And so the same is true for C. If we look at our limit, as n approaches infinity of n factorial over 3n factorial plus 5, we see very quickly that this is 3 times n factorial. It's going to shoot off toward maybe 0, get really close to 0. So let's see, that's going to tell me that this we again do not know. We don't know what's going to happen to it. So we need to do further tests. Our next way of telling convergence or divergence would be through our geometric series. Now, if you have an infinite geometric series and you have your ratio, in other words, what you are multiplying by each time, if that ratio is greater than 1, and again, here, absolute value greater than 1, then your sequence or series diverges. Now, if our ratio is going to be less than the absolute value is less than 1, then the series converges, and we can actually find what it converges to. Interestingly enough, it converges to this value. Now, this is one of the only series that we're able to do this with. And again, we have to make sure that ratio is bounded between positive and negative 1. So let's look at our first example and see if we can determine whether or not we converge or diverge. And if we converge, what does it converge to? So for A, looking at this, now some rewriting would help here. I would take this constant value of 5 and move this out. And so I have 5 times, and we have from n equals 0 to infinity of 1 over 3 to the nth. And this we can still rewrite as 5 times. And to me, the rewriting makes it a little bit easier for us to pinpoint, well, what would my ratio be? And notice we see that I can take this and really rewrite it as this. So notice what we're multiplying by each time. We're multiplying by 1/3. So let's see what our, notice that ratio is, the absolute value of 1/3 is less than 1. So we're ready to find what we actually converge to. We can do our sum formula, our first term, which our first term is going to be, let's see, 1/3 with the raised to the 0 power, so it's going to be 1 over 1 minus our ratio, what we're multiplying by each time. So I have 5 times 1 over, that's going to give us 2/3. And so 5 times 3 halves, or 15 halves. So notice we converge and we know what our sequence converges to. And this is one of the only ones we can say that with. All right, so very quickly, if you build off of what we just looked at, notice what this ratio would be each time. We're multiplying by 5/3. Well, the absolute value of 5/3 is greater than or equal to 1, so instantly we know this diverges. Our next type of series that we talk about would be called a p-series, and we really use p-series quite a bit. Now, in the p-series, we can test for convergence or divergence very quickly. If p equals 1, and we can kind of jump straight down to here, and then we'll come back up and talk about a harmonic series. But notice that if p is greater than 1, and notice that p is talking about your exponent here. If p is greater than 1, then the series converges. It diverges if p is bounded between 0 and 1 or equal to 1. So notice that up here, if p equals 1, this is a specific series called the harmonic series. And you can even generalize the harmonic series to look like this. At any rate, notice that we do diverge with that. So looking at our example 3, the harmonic series here, notice we're looking at 1 over n. And notice here our p-value is 1, so this series would diverge. Over here, p is 2, and notice that that means here p is greater than 1, so I have that my series converges. And it is really that simple. Okay, direct comparison test. And with the direct comparison test, it's very useful to use. Now notice it talks about different types of series comparisons here. How this is a geometric series, but this is not. This is a p-series, but this is not. But we can compare those. That's the whole idea of it. Now, in a sense, we have to keep in mind which of the series is bigger than the other. And notice here, A is less than B. So here, A is less than B. So if B converges, well, A is smaller, so it would also have to converge. And if A diverges, then B must diverge. And we've simplified it here to tell you that if the larger series converges, then the smaller series must also converge. But if the smaller series diverges, then the larger series must also diverge. So that's the whole idea with your direct comparison test, and this is something you'll use quite a bit. Okay, looking at another test, we have our limit comparison test, and the limit comparison test is another great quick way to go through and see what happens here. So you have to keep in mind that A and B are both greater than 0, and when you find the limit of A over B and you get a limit value that is finite and positive, then the two series will both converge or diverge. So let's see some examples with that. Let's look at example 3. It asks us to determine whether or not this series converges or diverges. Now, my series going off. So let's look and see right here. If we isolated just that one term, really that looks an awful lot like our series, and it's 1 to infinity of 1 over n. Looks very similar to that, and we know that this series diverges. So let's do our limit comparison test and see what happens. So let's do the limit as n approaches infinity, and we have 1 over 2n plus 3 over 1 over n. And notice how this ends up flipping over. And let's see, so we have the limit as n approaches infinity. And we have, let's see, n over 2n plus 3. And notice our infinite limits. We know that this answer is going to be 1/2, which is finite and positive. So both of these will diverge because I know 1 over n diverges, therefore this should also diverge. Okay, here's some more examples with this, with our limit comparison. And so going through here, we see, again, if we do the limit, it'd help if I got my pen to write. How about that? Woo! All right, so we have, again, the limit as n approaches infinity, and it tells us to compare this to 1 over n squared. So I have 1 over 3n squared minus 5n plus 7 over 1 over n squared. And very quickly we see how we have n squared over 3n squared minus 5n plus 7. And so as our limit approaches infinity, I get 1/3, which is positive and finite. And so therefore I know this converges, so therefore this should also converge. Right, so same idea over here on part B. We're going to work through and see, well, do we converge or diverge? And our limit comparison once more. So we have the limit as n approaches infinity. I have 1 over the square root of 4n minus 2 over 1 over the square root of n. So we end up with the limit as n approaches infinity, the square root of n over the square root of 4n minus 2. And if we just look at our dominating factors here, well, let's see, it looks like, just in our minds, let's think about the square root of n over 4n, where those n's cancel. So really I end up with 1/2, which is positive and finite. So I know this series will do whatever this one does. Well, this one, remember, we can refer back to the P series for this, and my exponent would be 1/2, so that is between 0 and 1. So this diverges, so the other also diverges. Okay, and continuing on with our comparison, if we compare this, we should get a finite limit, and this one would also converge, and our next one should also diverge. And let's work out this one just to make sure we follow the algebra in that one. So here we're going to go through and we're going to compare. And let's see, gosh, first, I don't know if this thing right here, I said it diverges, but I don't know. Let's think about why it would diverge. This is going to shoot off toward infinity. To me, a quick graph would help. If I look, because I need to know which of these two would be a larger value. Well, n squared, but then 2 to the n does something like that. So in my mind, 2 to the n, much larger. So this should shoot off to infinity, which means divergence. So let's compare and see what we have. So we have our limit. If I can get my pen back, that would be awesome. Okay, so we have the limit as n approaches infinity. And we have n times 2n 2 to the n over 4n cubed plus 3. And let's see, divided by, so I'm going to go ahead and flip this over. We have n squared over 2 to the n. And with some quick algebra, we see that here we'll end up with n cubed over 4n cubed plus 3. So this limit value is going to be positive and finite. Therefore, this does exactly what this one over here does. Therefore, it diverges. Okay, we are almost finished looking at some of these tests. And again, there's more tests, but I just picked on the ones that you see quite a bit more of. So one of them would be the alternating series test. And notice that the alternating series test, you have to make sure both conditions are met. And when the nth term goes to 0, and then the values are decreasing for all n values. So let's look and see. And so we're trying to determine what happens to this particular series. So the first thing we do is check our nth term. Well, our nth term, the limit as n approaches infinity of 1 over n, that does go to 0. So we've said, okay, that one works. Well, is the n plus first term smaller than the nth term? So they are decreasing in value as far as, notice our series, we have 1, and then we have 1/2, 1/3, 1/4, 1/5. So they are decreasing in value, so yes. So is the series going to converge or diverge? Well, it met both criteria, so converges. And the last one that we need to talk about is our ratio test. And this that we've already been doing, because I go a little bit out of order with this. This is what we've been doing to find our interval of convergence. Oh, my pen is freaking out. This is going to be interval of convergence. So you've already been working on this in class, and really we've focused on number 1. So that's the main focus here that we will see, and y'all can read through the other parts, and hopefully y'all have seen a little bit of a good little overview of this. Something we do need to keep in mind, though, this ratio test is inconclusive if our limit is equal to 1, which means we've got to go find another test to do.